Okay, this is Math 131, section 10.2. We're going to talk about first about finite mathematical system. Okay, so when we talk about a finite mathematical system, we're talking about a mathematical system whose set contains a finite number of elements. Okay, so remember we defined mathematical system as, a set with a binary operation. Okay, so we're talking about a finite mathematical system. The set is a finite number of elements. It's not going to keep going forever and ever, right? Okay, so let's first talk about clock 12 arithmetic. Okay, that's kind of like, we can also say that's like clock arithmetic. So we're going to use a set of elements 1 through 12. We're not going to have a 0. Okay. And then the binary operation that we'll use is addition. Okay. So when we go in movement clockwise, we're going to go 4 plus 9. Think about going around the clock. So 4 plus 9 is not going to be 13. It's going to be 1. Okay. Because we don't have a 13, right? So when you go around the clock and you move, now we're going clockwise, right? 4 plus 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, we get to 1, right? And then we can say 9 plus 4 is also 1. 9, starting at 9, we go 1, 2, 3, 4, we get to 1 o'clock, okay? So we also say 9 plus 4 equals 1, okay? And then on the next slide, we'll look at a table of what we get when we do this. Okay, and this is kind of a big table, but the idea is that once you get past 12, you start at 1 again, okay? So 1 plus 1 is the column of bold and the rows of bold, those are the numbers that we're adding using clock arithmetic. So we're going to add 2 plus 2, we get 4. So if you get something less than 12 or less, it's no big deal. But if you get 13, you have to change it to a 1. So all these 1s were 13s, right? Like 10 plus 3 or 9 plus 4 or 8 plus 5 or 7 plus 6. Okay. If you get to 14, you got to change it to a 2. Okay. So 10 plus 4, 9 plus 5, etc. If you get to 15, you got to change it to a 3. 16, you got to change it to a 4, etc. So basically, you're always going to get to a number that's between 1 and 12. Okay, 12 plus 12 is not 24, but 12. So if you get a number bigger than 12, you take away 12 to get your answer. Okay, so do you see how that table works? That when we add two numbers, we're going to get something between 1 and 12, because let's say 8 plus 12 is 20. Okay, 8 plus 12 is 20. We're going to take away 12 to get the 8 there. Okay, so we want to determine if this is a commutative group. Okay, so here's our set, the numbers 1 to 12. And we first want to check closure. Okay, now we're using our table, right? So, 5 plus 11 is not going to be 16. It's going to be 4. Okay, so we're going to take away 12 to get our answer. So we do have closure because when you add using clock arithmetic, when you add any two elements in the set, you're going to get a number between 1 and 12. Okay, so we do have closure under addition. Okay, identity element. Now, it's not 0 because we don't have a 0. It's actually 12. So if you add 12 to 4, you get 4, right? So our identity element is going to be 12 in this case. Okay. A little bit different than normal addition, right? Because we don't have a 0. Okay. So if you add 12 hours to 4 o'clock, you get 4 o'clock. If you add 12 hours to 3 o'clock, you get 3 o'clock. So that's the identity element there. Okay, inverse element. The additive inverse element is the number that when we add, we get the identity element, okay? So, which is 12, okay? So 8 is inverse is 4, okay? Because 8 plus 4 is 12, okay? So 4 is the additive identity of 8. No, it's, we have negatives, right? Okay. And then we can look at like 7 and 5. So the additive identity or inverse element of 7 is 5. That will give us to 12, which is our identity element. Okay. So we have to think about what gets us to 12. For 7, it's 5. Okay. For 8, it's 4. For 9, it's 3. Okay. So let's look at the table of those in the next slide. Okay. So for 1, its inverse is 11 because we have to add to get to 12, right? For 2, it's 10. For 3, it's 9. For 4, it's 8. For 5, it's 7. For 6, it's 6. It's its own element, right? For 7, it's 5. For 8, it's 4. For 9, it's 3. For 10, it's 2. For 11, it's 1. And for 12, it's 12. Okay. Notice 6 and 12 both have their own element as its own inverse. Okay. See, we're trying to get to 12, right, which is our identity element. So that's how we have the inverse element. Okay. Okay, now let's check associative property. Okay. Now we're doing addition, but we're doing clock addition. So for all values of a, b, and c, does a plus b plus c equals a plus b plus c if we do a plus b first or b plus c first? Okay, so we do this by example. Okay, so let a equal 2, b equals 6, and c equals 8. Okay, so we have 2 plus 6 plus 8 using 2 plus 6 first, and then 2 plus 6 plus 8 using 6 plus 8 first. Okay, 2 plus 6 is 8 in clock arithmetic, so we have 8 plus 8, right? And then 6 plus 8 in clock arithmetic gives us 14 minus 12, which is 2, right? So we have 2 there. So now we have 8 plus 8 equals 2 plus 2. Now this is not normal addition, right? We're not, 8 plus 8 normally is 16 and 2 plus 2 is 4, so that's not true. But in clock arithmetic, when we add 8 hours to 8 o'clock, we get 4 o'clock, right? 8 plus 8 is 16 minus 12 is 4. Okay, and then 2 plus 2 is 4. So this is true. Okay, and if we try other elements, we'd have the same result. So we do have the associative property under addition. Okay, so now we have a group because we've tested those 4 properties. But we want to make sure it's a commutative group. Okay, so for all values of a and b, does a plus b equal b plus a? Okay, so let's try couple examples. 5 plus 8 equals 8 plus 5. 5 plus 8 is 13. Divide minus 12 is 1, right? And 8 plus 5 is 13 minus 12 is 1. So we get 1 equals 1. That's true. Remember, we're doing clock arithmetic. 9 plus 6 is 15. Minus 12 is 3 in clock arithmetic. 6 plus 9 is 15. Minus 12 is 3 in clock arithmetic. So that's true. Okay. And if we were to try other elements, we would have the same result. So commutative property is true. We're just looking at a couple examples, showing it by induction. Okay, and since all of the 5 properties were satisfied, this is a commutative group. Okay. If the first 4 properties were satisfied, we'd say we have a group, but because it's commutative also, we have a commutative group. So we can say clock 12 arithmetic under the operation of addition is a commutative group, and sometimes we use that word abelian group. It just means commutative group. Okay, a couple things to recognize. For the associative property, if not every element in the set appears in every row and every column, you need to check that associative property carefully, okay? So we have to check more than one example, okay? But if you have every element in every row and every column, it appears in every row and it appears in every column, then you can just check the associative property once and it looks good, okay? Also, for commutative property, if the elements are symmetric across the main diagonal, then it's commutative, okay? Now, we can have groups that are non-commutative, okay? And we call those non-commutative or non-abelian groups. Now, that means it does have the associative property, but it doesn't have the commutative property. So we'll look at an example of that in class. Okay, now let's look at an example where we're using a symbol for our operation, okay, and which would be this number symbol, and our elements are going to be something weird like capital P, capital W, and the @ symbol, okay. So we're doing something a little bit different. So we're going to use this mathematical system. We're going to look at the set of elements, the binary operation, whether we have closure, the identity element, and the inverse. And we're going to look at see if we have associative property and commutative property for F and G using these 2 examples. Okay, so you're going to see a table like this. This is our operation. Okay, that thing in the upper left corner. These are our elements: the @ symbol, the P, and the W capital. Okay, see they're going across and they're going down. Okay, so now we can say like number @ this is our operation. So it's like 2 plus 3 or 2 plus 2 gives us P. All right. P number @ gives us W. P number W number @ gives us @ okay, and then we can do it for every other operation, for every other row too. So @ number P gives us W, @ number W gives us @ P number @ gives us W, P number P gives us @ P number W gives us P, W number @ gives us @ W number P gives us P, And W number W gives us W. So what you can do is you can kind of go across, you know, this is our operation, and if you go across this row and across this column, you'll see the results, okay? So our set of elements is that at symbol, the P and the W, okay? And the binary operation is that number symbol, okay? The table contains only the elements of at, P, and W, so it is closed, okay? So we do have closure, we can see, because we don't have anything else in our table. These are our results when we do, you know, any binary operation. So it's always one of the elements. So we do have closure there. Okay, now let's check the identity element. If I want to go to start with at and do a number operation, do that number operation, to get back to at, I have to go to W, right? So at, we can say this, I'll show the operation, but it's at number W equals at. See, we're getting back to where we started. And then we can also look at P. P number W gives us P. See, it gives us the same thing. Okay, and then W number W gives us the same thing we started with, which is W. See, so we can see that this is our identity element. Okay, is W. Okay, so that's how we find our identity element. Okay. Now for inverse element, we want to get back to this identity element. Okay. So at number what gives me W? Well, that would be P. Okay, so at number P gives us W, right? Which is we're trying to get to the identity element. So the inverse of at is P. And we can also show, like, the inverse of P, now we want to get to W, right? P number at is W. So the inverse of P is at, okay? And then W number what gives me W? It's W. So W is its own inverse. W number W equals W. Okay, so those are the other things that I'll write these down. P number at gives us W. So that's the inverse for P. That should be an at. Ampersand, whatever you want to call it. Okay, and then W number W equals W. Okay, so these are, I'll put the inverses in red. Okay, the inverse of P, sorry, the inverse of at is P. So the inverse of at is P, right? Because if I say at number P, I get my W, which is my identity element, right? The inverse of P is at, because if I take P number at, I get my identity element of W. Okay? And the inverse of W is W, because if I take W number W, I get my identity element. See, we're trying to get to our identity element, which is W, for each of these cases, right? So we're going to combine it with whatever gives us that identity element, which is, in this case, for at it's P, for P it's at, and for W it's W. Okay, so that's how we find our identity, our inverse. It's a little bit, a little tricky to do that sometimes. Okay, now we're testing the associative property. We're going to see if at number P, doing these two first, is the same as at number P, doing these two first. Okay, so we're going to do at number P first in the parentheses on this side. Okay, which at number P gives us W. Okay, so that's W, and then we're going to do the number P for that. Okay, and then here we're going to do the P number P. So P number P gives us at. Okay, so we're going to see if W number P is the same as at number at. Okay, so W number P gives us P. Okay, and at number at gives us P. Okay, so these are the same. So we do have the associative property in this example, at least from the example we checked. Now, you can also do this. Well, we checked it once and it seemed to work, but also see if every element's in every row and every column. Here we have all three in this row, all three in that row, all three in that row. And look at the columns. All three in that column, all three in that column, all three in that column. So we can pretty safely say that the associative property is satisfied here, which means we do have a group. Okay. Now let's talk about commutative group before we move on to the last slide. If you look at your, and I'll do this kind of, if you look at your diagonal, okay, if you kind of draw a line through it, you see if it's symmetrical about the diagonal. Okay, so you see how it's it's these reflect and these reflect and these reflect. We have symmetry about the diagonal. Like this reflects to this reflects to that, and this reflects to that, and they're the same. So that means we do have the commutative property. But let's test our last example just to verify that. Okay, so the last thing we're going to see if W number P equals P number W. Okay, so W number P is P. Okay, and then P number W is also P. So we have the commutative property satisfied there. Okay, and we'll look at different examples of groups in class. I know it's a little awkward, but this number thing is our operation, you know, and these are the things we're doing the operation with. Okay, with these symbols. Okay, so we're going to use different symbols for our operation and maybe different symbols for our elements of a set. But this one, you know, it's a finite mathematical system, and we showed that it's a group. And in showing commutative property, we've also showed that it's a commutative group.